Welcome to the deep dive. You sent us a stack of intelligence briefings, research papers, and market analyses, and wow, they are screaming one collective message. The quantum AI nexus has fundamentally broken its own timeline.
It really has. I mean, over the last 48 to 72 hours, we have witnessed a dramatic, measurable shift.
Absolutely. The story is no longer about the theoretical promise of quantum computing in, what, a decade from now? It's about verifiable, quantifiable advantage right now.
And its industrial scale integration is becoming the essential, non-optional accelerator for artificial general intelligence, or AGI.
That captures the urgency of this material perfectly. For years, quantum computing felt like this perpetual research project, right? A science fair experiment trapped in a cryostat.
Exactly. But the focus has fundamentally shifted. It's not about mere qubit counts anymore, which were often noisy and fragile. What we're tracking today are concrete engineering milestones.
Real breakthroughs.
Real breakthroughs in real-time error correction, staggering hardware fidelity, and hybrid algorithms that are just demonstrably shattering classical computational limits.
So our mission today is crucial. We're going to filter through all this high-speed technical news flow and pull out the specific quantifiable nuggets.
The proof points.
The proof points that prove quantum technology is moving decisively out of the academic lab and into the industrial infrastructure that you need for the next generation of AI. We're looking for proof that this stuff is resilient, scalable, and, commercially useful.
Precisely. And before we dive into the specific numbers, we have to establish the core relationship described across these sources, because it's this beautiful symbiotic feedback loop.
Okay.
This convergence is defined by two roles. You have AI, which is the glue or maybe the immune system for quantum hardware.
And then on the other side.
Quantum is the accelerator for AI training.
Okay, let's unpack this synergy. What does that AI as glue concept really entail? Why is it so indispensable?
Well, the AI as glue idea is arguably the most critical engineering development we've seen. Quantum chips are just inherently fragile.
Right, the whole decoherence problem.
Exactly. Their computational units, the qubits, they lose their quantum state almost instantly because of environmental noise. I mean, computations can crash in microseconds. The breakthrough is deploying advanced AI, specifically reinforcement learning agents, and these recurrent transformer neural networks.
And they act as what? A high-speed immune system?
That's a perfect way to put it. This AI is constantly monitoring the quantum chip for noise, for specific quantum errors, in real time.
So it's catching and fixing them.
Faster than they occur. It effectively stabilizes a fundamentally unstable system. It turns a fragile physical resource into a reliable logical one. Without that AI glue, the quantum computer is just this brilliant but non-functional machine.
So the AI keeps the quantum computer from crashing, which lets it run these long, deep calculations. And then the quantum computer, the accelerator, repays the favor by turbocharging the AI itself.
That's the loop. And this is why it suddenly matters so much for AGI. Because the path to AGI scaling, it hit a wall.
The energy wall.
The energy wall, or the computational limit of classical optimization. Current large language models, they're impressive, but they rely on classical techniques. And they fundamentally struggle to model the physical world with high fidelity.
Especially complex, chaotic systems. Things like molecular interactions or material science.
They're magnificent at correlation, but they are weak at causation in the physical realm.
Right.
Correct. So quantum is stepping in to solve those previously mathematically impossible problems. It allows for the perfect simulation of chemistry and physics, something classical computers simply can't do efficiently because of the exponential complexity.
And that's the high-stakes mission here. We're not just building faster versions of ChatGPT, we're building a data factory that can simulate reality perfectly.
And that synthetic, high-fidelity physical data is what's going to train the next generation of true world models.
Letting AI bypass its current reasoning plateaus in scientific discovery, allowing them to predict outcomes in materials or biology with, unprecedented accuracy.
The ability to simulate reality efficiently means that AI can learn from a perfect, synthesized environment. This training data is just so much more valuable, so much richer than just learning from human-labeled text data.
Which is inherently flawed and incomplete.
And limited by our own understanding of the world. This is the path to truly generalized intelligence.
Okay, let's start with the hard, undeniable numbers. The metrics that signal the end of the noisy experiment era. We have to dive into Google's breakthrough with the Willow chip and the quantum echoes algorithm. This isn't just fast, It feels like a category-defining moment.
It really is. It's the point where quantum speedup stopped being this theoretical promise and became a proven industrial metric. Google's 105 qubit Willow chip, it executed the quantum echoes algorithm and achieved a monumental 13,000x verifiable speedup.
13,000.
But let's clarify the scale of that for you.
Right, that's the critical comparison point. What exactly is being contrasted here?
We're contrasting it against the world's most powerful classical supercomputer, Frontier, an exascale machine. The simulation was completed on the Willow chip in about 2.1 hours.
2 hours. And Frontier would take?
Over 3 years. To complete that exact same calculation simulating complex physical phenomena, Frontier would have to run continuously for over 3 years.
Wow. That's not a marginal improvement. That is an exponential decoupling from classical constraints.
The difference between 3 years and 2 hours makes previously inaccessible science suddenly actionable.
3 years versus 2 hours. That truly is a different universe of computation. What's so crucial here, though, is the word verifiable. We've heard about quantum supremacy claims before based on random circuit sampling, which is, mathematically interesting but scientifically useless. This is different.
Oh, it is fundamentally different. Quantum supremacy used these random benchmark problems designed just to prove the quantum computer could do something a classical one couldn't easily check.
A party trick, basically.
A very expensive party trick. The quantum echoes result, however, is a verifiable result that yields repeatable physical predictions. They were simulating complex atomic interactions, specifically the dynamics of a spin glass model.
Which is critical for material science chemical reactions.
Molecular dynamics, yes. This transition to verifiable utility for scientific problems directly relevant to AGI training. It confirms we have officially entered the age of beyond classical computing.
And this speedup wasn't just raw quantum power. It needed that AI glue we talked about. What was the AI doing to make sure a 2-hour computation didn't just crash in the first microsecond?
The key enabling technology was the alpha-qubit decoder. This is an advanced AI component, a recurrent transformer neural network, specifically trained to identify and mitigate the unique noise profiles of these superconducting qubits.
So it's constantly course correcting.
Constantly. You cannot run a complex, multi-layered circuit for 2.1 hours without intelligent stabilization. The alpha-qubit decoder works in real time, ensuring the computation stays alive and coherent long enough to deliver that groundbreaking result.
It's what turns the raw, noisy qubits into a coherent, useful resource.
It's the core mechanism that validates the whole synergy of AI and quantum.
Okay, let's pivot to the second major hardware barrier that just collapsed.
Yeah.
The room temperature revolution. I mean, for decades, quantum computing was synonymous with these massive, power-hungry cryogenic refrigerators.
Keeping qubits near absolute zero.
Right, and Stanford just circumvented that entire logistical and energy overhead.
They did, and the implications for industrialization are truly staggering. Stanford researchers achieved the successful entanglement of light and electrons at room temperature. They used a compact hybrid system, employing twisted light, a specific type of chiral light in molybdenum diselenide, or MOS, silicon chips.
Okay, that technical detail, MOS chips and twisted light, sounds a bit abstract. Can you break down why that specific setup works without supercooling?
Absolutely. The MOSARs acts as a semiconductor interface. They aren't trying to cool the entire atom. They're using this twisted light to transfer angular momentum to the electrons within the chip.
So it's creating a spin state that can be entangled with the light itself.
Exactly, with the photons of the light. This light-matter interaction, it's happening right at the interface of the material, and it's highly energy efficient. And crucially, it's stable enough to maintain that entanglement coherence at ambient temperatures.
So if you remove the need for massive cryogenic infrastructure, the power budget, the physical space, the complexity, you're removing the single biggest hardware bottleneck for deployment.
That's the profound implication. It potentially slashes quantum AI deployment timelines by a decade because it standardizes the infrastructure.
A decade.
Think about traditional data centers. Instead of needing this massive multi-million-dollar quantum facility attached, future AI models could use hybrid quantum classical chips integrated directly into standard server racks.
Which would allow for rapid, modular deployment of these quantum accelerators for specific tasks.
Like rapid neural network training, specific optimization algorithms, or high-dimensional gradient descent calculations. It makes quantum resources accessible and scalable globally.
So if Google is proving speed, and Stanford is proving accessibility, the final piece of the hardware puzzle is quality. The building blocks have to be perfect. Let's talk about the qubit quality standard set by Silicon Quantum Computing, or SQC. That 99.99% fidelity. That seems to be the precision you need for AGI-level reliability.
That 99.99% fidelity milestone, specifically in a silicon-based architecture, is a monumental feat of engineering. Fidelity, for you listening, is the reliability of a quantum operation.
The chance that your instruction actually does what you told it to do.
Precisely. If fidelity's low, errors just accumulate instantly. Achieving 99.99% means that for every 10,000 instructions, only one gets corrupted. This is the ultra-high precision you need for the complex error correction codes to even work.
So in classical terms, that's the difference between a reliable supercomputer and one that just crashes every few minutes because the transistors are flaky.
Exactly. But here's the crucial point, the scaling secret they detailed in their publication. This ultra-high fidelity was shown to stay stable or even improve as more qubits were added to the processor.
Wait, that defies the usual curse of complexity. Normally, adding more qubits means exponentially more noise, more interference.
And a rapidly dropping fidelity.
So why did silicon defy that expectation?
It validates the inherent stability and isolation you can get with spin qubits built inside these highly controlled industrial silicon processes. If the quality of your fundamental building blocks stays constant or improves as you scale up, you've overcome the single largest bottleneck in building fault-tolerant quantum computers.
And that stability is the prerequisite for hosting the complex logic and memory that a massive AGI needs.
It is. This is why silicon is rapidly moving from niche research into an industrial necessity for large-scale, fault-tolerant quantum hardware.
Okay, so if the first section was about faster, more accessible, higher quality building blocks, this next section is about making sure the massive structure you build from them doesn't just collapse. We have to talk about fighting decoherence.
The AGI immune system.
Exactly. The software and hardware mechanisms that ensure quantum calculations can actually run long enough for AGI scale operations.
Right. The whole shift from using fragile physical qubits to robust logical qubits is entirely dependent on mastering error correction. For AGI to get any utility out of this, we need logical qubits.
Fault-tolerant, resilient.
Built out of dozens or even hundreds of noisy physical qubits that can run deep, sustained computations for hours. This requires sophisticated self-healing systems.
And the most exciting breakthrough in that self-healing capacity seems to be pure speed. Riverlane's local clustering decoder, the LCD, is being called the microsecond error killer.
And that description is apt. Riverlane's LCD is the first hardware-based decoder to correct quantum errors in under 1 microsecond. Astonishing.
Under 1 microsecond. What were we looking at before?
Previous generations of decoders often took 10, maybe even 100 microseconds to process and fix an error. This delay created a backlog of accumulating errors. If the noise arrives faster than you can fix it,
The computation is doomed.
it's doomed to collapse. So the 1 microsecond threshold isn't just a technical detail, it's a physical necessity.
It's the difference between a broken system and a self-correcting one.
It creates what we call the reflex arc. This speed is fast enough to fix errors faster than they physically occur. The LCD uses an FPGA, a specialized high-speed circuit with what they call an adaptivity engine that learns the quantum chip's specific noise fingerprint in real time.
The significance of that speed. It's like the difference between seeing a problem and having your hand instantly yanked away from a hot stove. If you eliminate the problem of errors piling up, what does that enable for AGI?
It enables what we call infinite depth circuits. It means the quantum computer can theoretically run a sustained, coherent calculation for hours, even days, as required for these complex AGI training tasks.
And crucially, our sources say this breakthrough potentially quadruples existing hardware power.
It does. How?
How does fixing errors faster lead to a 4x power increase?
It reduces the physical qubit overhead, the number of physical qubits you need to form a single logical qubit. If your error rate is lower, you don't need, say, 1,000 physical qubits to stabilize one logical one. Maybe you only need 250.
So by reducing that overhead by 75%, you unlock the latent power of the physical machines we already have.
Exactly, moving them closer to being truly fault-tolerant and useful for production-level AI optimization.
So AGI needs a self-healing machine. And this brings us to the AI component itself, the reinforcement learning tutor. The idea that an AI agent is effectively playing a video game to teach itself physics stabilization. It sounds like science fiction, but it's real.
It's an elegant solution to an incredibly complex problem. Quantum noise patterns aren't uniform, they're chaotic. They depend on temperature, magnetic fields, local defects.
So a human engineer can't possibly code for every scenario.
They struggle to. So researchers use a reinforcement learning agent that learns to fix these errors by treating error detection and successful correction as a high-value learning signal. The agent gets a reward, or points, for every cycle it stabilizes the system.
It's optimizing for persistence.
Yeah, precisely. And after playing this stabilization game in simulation millions of times, adapting to every conceivable type of noise, the AI achieved a demonstrable 3.5-fold improvement in error rate stability compared to expert human-designed, hand-tuned code.
And a 3.5x improvement in stability is not a marginal gain.
No, it's a necessary condition for AGI. It guarantees that persistent, coherent state you need for running those enormous variational solvers and optimization algorithms that AGI requires. It creates the never-stop computing paradigm.
Meaning the quantum machine is always available, always stable.
And always ready to serve the AI architecture that calls on it. It solves the problem of the quantum computer being this temperamental device that only works perfectly 10% of the time.
So we're seeing different companies approach stabilization from two angles. The fix-it-fast approach from Riverlane, and then there's the born stable approach. Tell us about Microsoft's Majorana One chip and their topological strategy.
Microsoft's approach, using these exotic particles called Majorana fermions to create topological qubits, is a long-term fundamental bet. These qubits are designed to be born stable.
So instead of constantly fixing errors, you design the qubit so it's less likely to make an error in the first place.
Exactly. Unlike traditional qubits where the quantum information is stored locally, like the spin of a single electron, Majorana information is stored non-locally, across the geometry, the topology of the system.
That sounds like a physical safeguard. If one spot on the chip gets hit by noise, the information is still safe because it's distributed.
That's exactly right. They are inherently resistant to local environmental noise. Their internal reports suggest their Majorana One chip is entering this crucial, long-lived logical qubit phase. The goal here is strategic: to remove the massive AI overhead you currently need to fix errors, simplifying the entire quantum stack.
It's a strategic choice. Either invest in a machine that needs a huge AI security team, or invest in a design that's self-securing from the ground up.
And we're seeing commercial convergence, too. Take Quantinuum. They're focused on advanced software solutions using high-performance ion traps. Their machine, Helios, is making huge commercial progress in error correction.
Their roadmap's projecting.
They're projecting the near-term feasibility of creating up to 1,600 logical qubits that function reliably. So both strategies, the fundamental stable design of Microsoft and the advanced software correction from Quantinuum, are converging right now, proving that the pathway to reliable, large-scale quantum resources is viable across multiple physical modalities.
Okay, so we've established unprecedented speed and proven stability. But AGI demands massive computational power. We need millions of qubits, not hundreds. And the traditional challenge has always been that physical wiring bottleneck in 2D chips.
That's the major industrial hurdle. If you try to pack millions of qubits onto a single flat chip, you face two immediate ruinous problems. First, interference or crosstalk just ruins the calculation.
And second?
The sheer volume of wiring you need to control and read out millions of qubits becomes an unmanageable spaghetti mess. It physically blocks connectivity and generates heat. This is why the industry has so aggressively pursued 3D stacking solutions.
And the architecture firm Quantware seems to be providing the crucial solution with their VIO 40K architecture. What makes this 10,000 qubit design the vertical city that breaks that 2D limit?
The VIO 40K uses two key elements from classical semiconductor manufacturing: TSV, or through silicon via, and chiplet designs. Think of a traditional chip as a sprawling ranch house where all the connections are on the ground floor.
Right. When you add more rooms, the hallways get impossibly long and crowded.
Exactly. The 3D stacking is the skyscraper. TSVs are these tiny vertical electrical connections etched straight through the silicon chip, allowing communication and control lines to be routed vertically instead of horizontally.
And that density allows for,
40,000 I/O lines on a single stacked chip. It completely solves the wiring bottleneck that plagues older 2D designs and lets them scale to 10,000 qubits in a small, dense, manageable footprint.
And crucially, this isn't happening in a vacuum. This is happening in partnership with key classical hardware makers.
Yes, the partnership with NVIDIA via NVQLink is a massive signal of industrial maturity. These processors are being explicitly designed as modular quantum GPUs.
So an AI architect doesn't have to learn a completely new programming stack.
Exactly. They can call quantum subroutines directly from a standard AI training loop using the same interfaces they use for calling classical GPUs. This makes the quantum accelerator a practical modular reality for hybrid clusters. It just significantly shortens the timeline for embedding quantum power into existing AGI data centers.
Meanwhile, IBM and UC Berkeley are focusing on the internal blueprint for scaling, specifically mitigating that crosstalk interference.
They are providing the architectural roadmap needed to move toward their future multi-million qubit design, the Starling architecture, which is targeted for 2029.
So how are they dealing with crosstalk?
IBM is using advanced AI simulations to predict and block this interference before it happens. They're optimizing the layout of the qubits and the control pulses. Essentially, they're using AI to create the perfect soundproofing for their city-sized quantum processors.
And how far along are they in running the deep circuits that AGI needs? I mean, running deep algorithms requires a lot of gate operations.
The progress is phenomenal. IBM's current ability, which is driven by their Relay BP AI-driven decoder, can run circuits with over 5,000 2-qubit gates.
5,000.
To put that in perspective, a few hundred gates was considered the limit before errors just overwhelmed the system. Achieving 5,000 gate depth demonstrates how these AI control systems are immediately unlocking the vast potential of the hardware we have right now.
It validates the whole architectural approach.
It does. It validates the approach needed for building fault-tolerant, massive arrays capable of hosting sophisticated AGI algorithms.
Okay, finally, let's look at the massive financial and government support for making these things cheap and ubiquitous. The Democratizing the Qubit initiative in Texas. This isn't just about scaling the number of qubits, it's about scaling the availability.
This is a critical strategic bet on mass production. The huge grant from the Texas Semiconductor Innovation Fund is aimed specifically at building CMOS-compatible quantum chips.
Which means forcing quantum manufacturing into standard semiconductor foundries.
The exact same infrastructure used to mass-produce chips for your phone or your laptop.
And what's the economic driver behind that?
Extreme economic scale. The goal is to lower the cost of a single qubit from, say, $10,000 down to as little as $10. If you can leverage the existing highly optimized semiconductor supply chain, you achieve cost parity.
And if you make quantum hardware as cheap and accessible as GPUs,
you remove the cost barrier for integrating quantum accelerators into every data center, every research lab, and eventually even specialized edge devices. This level of democratization is essential for achieving the computational bandwidth needed for widespread AGI development and deployment.
So we've established that the hardware is verifiably fast, stable, and architecturally scalable. But is it doing real work right now? This next section is all about where quantum acceleration is delivering proven results, immediately moving the AGI timeline forward. The first big area is the drug discovery accelerator through QML embeddings.
This is a powerful demonstration of hybrid utility for a high-value AGI application. A new quantum machine learning framework was just unveiled that optimizes quantum data embeddings for ligand-based virtual screening.
So drug discovery is like finding the right key, the ligand molecule, to fit a specific biological lock.
Exactly, a viral protein or a receptor site. Classical systems are just brute forcing the problem. They run billions of computationally heavy simulations to see which keys might fit.
But QML embeddings are smarter than that.
They enhance the feature space dimensionality. It's like having a perfect X-ray vision map of the lock that tells you the precise geometric shape and electrical charge patterns. By using these hybrid neural quantum circuits, they extract features from molecular data that are just invisible to classical algorithms.
So they aren't just faster at checking keys, they're smarter about the underlying molecular geometry. The AI isn't wasting time on chemically implausible solutions.
Precisely. And this framework has demonstrably outperformed classical methods on difficult, real-world datasets, including screenings related to LAT-PCBA and COVID-19 drug targets. This acceleration is feeding high-fidelity, high-precision data directly into AI learning systems.
Addressing the data scarcity and data quality issues that plague this kind of modeling.
It does, and the capability is scaling beyond just small molecules. The sources highlight the first successful quantum-centric simulation of the Trep cage mini-protein.
Which is a genuine milestone because it involves protein folding.
Right. The Trep cage simulation successfully handled the complex interactions of hundreds of atoms via these hybrid quantum classical workflows. This is where quantum computing transitions from abstract calculation to industrial scale utility. Protein folding is one of the most computationally complex problems there is.
And for AGI, this removes classical limits in biochemical reasoning. It gives the AI the ability to model complex biological processes accurately.
A non-negotiable necessity for building an intelligent, world-aware model capable of, say, designing entirely new functional enzymes from scratch.
Okay, moving into even more abstract territory. Modeling complex dynamics. We're talking about protein folding and other chaotic, time-dependent systems, the kind of stuff designed to break supercomputers.
Yes. And key research on adiabatic quantum state preparation using Rydberg atoms is critical here. Adiabatic quantum computing is a method where you start the system in a simple known ground state and then slowly, smoothly transition it to the desired complex final state.
Following an energy landscape.
Exactly. And that slow and smooth transition is important because it minimizes errors. It supports hybrid simulations for problems like protein folding by enabling low-error evolution around phase transitions, where the system is highly sensitive to noise.
The ability to control those Rydberg atoms with high fidelity translates directly to stable exploration of these complex energy landscapes.
It does, and we also see this crucial theoretical bridge being built with the unified energy framework.
Which is mathematically elegant.
It frames spike trains, how neurons communicate in the brain neural networks, and classic optimization algorithms as processes that are all mappable to QUBO.
Quadratic unconstrained binary optimization, which is the mathematical structure that many complex optimization problems naturally fall into.
And quantum annealing machines, like those from D-Wave, are perfectly designed to solve that specific mathematical structure. By mapping these diverse processes to QUBO, this framework bridges neuroscience to quantum AI. It suggests that quantum hardware can handle the complex, entropy-minimizing computations that truly resemble brain-like processing and decision-making far better than classical architectures.
The core mathematical unlock for bio-inspired AGI.
It is.
Okay, finally, we have to address the most significant algorithmic barrier for scaling quantum neural networks. The QML backpropagation moment. I mean, the LLM revolution was defined by our ability to efficiently calculate gradients using backpropagation. Can we do that with quantum circuits?
This was the major roadblock, the barren plateaus problem. When you try to train a massive QNN, the complexity means the learning signal, the gradient, often just vanishes into noise.
And the training just stops dead.
It stops dead. But this new paper demonstrated a solution. They presented a method to train quantum circuits beyond classical simulation limits by using a symbolic propagation technique.
So instead of relying on expensive, repeated physical measurements of the quantum state to estimate the gradient,
Which is what usually costs exponential time.
they derived an efficient symbolic representation of how a change in a parameter affects the final output.
Precisely. The AI model calculates the learning gradients mathematically, reducing the need for all that massive classical verification overhead. This is the mathematical unlock that allows quantum neural networks to scale like traditional deep learning models.
Which means AGI architects can pre-train massive quantum generative transformers on vast data sets before the physical hardware even exists.
Accelerating the software readiness for the next generation of models that will run on those 10,000 qubit systems we discussed.
So we've seen the hardware speed up, the stability kick in, the architecture scale up, and the utility proven. Now let's synthesize this and look at the strategic and financial pressures driving this. The AGI race is clearly a winner-take-all full-stack race, and we saw Amazon make a major pivot reflecting this.
Amazon's consolidation of its frontier AI teams, its custom silicon teams like Trainium and Graviton, and its quantum computing division, Bracket, all under single leadership. That's the strongest possible signal.
It mirrors what we've seen from Google DeepMind and IBM.
It's an acknowledgement that NGI is a full-stack hardware intelligence problem. You can't just rely on external plug-and-play quantum hardware in the future. You have to integrate quantum acceleration deep into the core silicon and the training frameworks.
So quantum is now a non-optional first-class component of advanced AI development.
And that strategic decision is driven by the reality that they need hybrid performance to train the next generation of models efficiently, which brings us to the hybrid LLM expansion we're seeing commercially.
Right. Companies like IonQ and Quantum Basel are focusing specifically on optimizing the training of massive trillion-parameter LLMs.
Traditional LLM training involves these massive optimization problems, many of which are non-convex, meaning they have huge energy landscapes with many suboptimal local minimums.
And classical optimization just gets stuck in those local traps.
Exactly. Quantum machine learning is highly effective at exploring these non-convex problems to find the true global minimum much faster. This marks the transition of QML from an academic curiosity into a production-level tool focused on reducing the enormous energy and time cost of training the largest AI models.
Quantum is moving from R&D expense to a CapEx efficiency tool.
It is. And here's where the roles start to flip in the most fascinating way, proving the synergy. We talk about AI as the glue for quantum, but now AI is becoming the sophisticated quantum compiler itself.
Enabling this effortless sim-to-real transfer. The benchmark results for GPT 5.2 are truly remarkable.
They force a complete recalculation of AI capabilities. The OpenAI Frontier Science Benchmark revealed that GPT 5.2 scored an average of 92% on doctoral-level scientific reasoning tasks.
92%. That's significantly surpassing the 70% expert human baseline. And it included complex tasks in quantum electrodynamics.
Yes, QED and quantum field theory. So what we have is an AI that has effectively mastered the rules of quantum mechanics just by processing text and data.
This confirms that the latest frontier models can now understand quantum logic, identify optimal experimental setups, and serve as a high-level compiler for quantum hardware.
An AI that can write valid, optimized quantum code and solve doctoral-level physics problems is the perfect, scalable architect for the next generation of quantum chips and algorithms.
And the hardware community is preparing a massive, advanced playground for this super smart AI. Let's look at Fujitsu's training playground.
Fujitsu's launch is highly strategic. They've unveiled a high-fidelity, high-performance 10,000 qubit simulation environment.
This isn't just a simulator for testing, it's a massive data generation engine.
Exactly. It allows AGI architects to pre-train quantum neural networks on massive, noiseless data sets. This means they can perfect the software and algorithms for a 10,000 qubit machine before the physical, fault-tolerant hardware even exists.
It accelerates the software side of AGI by decoupling algorithm design from hardware availability. The AI can learn to fly the 10,000 qubit jet perfectly in a high-fidelity simulator before the engine is fully assembled.
This dramatically shortens the time between hardware delivery and immediate utility. It eliminates that slow, iterative process of designing algorithms for noisy hardware.
And this incredible convergence of technical capability and strategic foresight is translating directly into financial confidence. Let's close this deep dive by following the money. We are seeing the smart money pivot away from traditional cloud giants and into pure-play quantum hardware.
This is maybe the most tangible market signal. Financial data shows top-tier hedge funds like Citadel and Millennium are reducing multi-billion-dollar positions in traditional tech, in some cases selling Amazon stock, to aggressively buy into pure-play quantum hardware companies.
A perfect example is Rigetti Computing, whose stock has skyrocketed 3,000% recently.
And why are the smartest funds abandoning established, profitable tech for what was considered a risky R&D bet just a year ago?
Because quantum has moved from R&D speculation to an industrial CapEx requirement.
The market believes the hardware breakthroughs we discussed. Speed, stability, scale are real and will soon start generating significant revenue. They're anticipating that every major industrial and AI player will need to buy quantum accelerators.
And the quantum stocks themselves are rallying, not on hype, but on actual utility.
That's the key distinction. We're tracking massive rallies in companies like D-Wave, up 19%, and Rigetti, up 14%, that analysts are attributing specifically to commercial sales momentum.
D-Wave's pivot to offering logistics AI, using quantum annealing for real-time supply chain optimization, that's finally generating the concrete, measurable revenue that Wall Street demands.
It marks the definitive shift from the speculative era to the utility era for quantum. Capital is flowing because the hardware is starting to deliver measurable commercial value directly into global AI systems and industrial optimization.
This has been an incredibly detailed deep dive into a field that is just evolving at light speed. To synthesize what we've learned, I think the core takeaway is that the technical barriers, noise, speed, and scalability are falling not one by one, but simultaneously.
It's a coordinated attack on the classical computational wall, and it's largely driven by AI acting as that self-healing immune system for the quantum hardware.
The combined effect of the sub-microsecond error decoder, the 99.99% stable silicon, the 3D stacking, it means we now have a resilient, powerful, and increasingly accessible quantum resource.
The AI-driven stabilization ensures these deep computations can run long enough to matter, making quantum ready to accelerate that final push toward AGI.
And the ultimate goal of this convergence isn't just about faster calculations for better spreadsheets. It's about building a fundamentally better kind of intelligence, one grounded in a perfect understanding of the physical laws of the universe.
That's absolutely right. The convergence means we are building a data factory that generates the synthetic, high-fidelity physical data molecular simulations, complex dynamics, high-precision atomic interactions that are necessary to train truly intelligent world models.
It gives AGI a perfect training ground in physics and chemistry, information it could never get just by reading flawed human-generated data. This is what unlocks true scientific reasoning capability in AI.
It is.
So here's our final provocative thought for you to chew on. If we now have an AI model like GPT 5.2 that can achieve 92% mastery of doctoral-level physics, and we give it a massive, noiseless, 10,000 qubit simulation playground provided by Fujitsu,
What is the first scientific discovery that AI will make autonomously without any human guidance that is genuinely new?
and perhaps more importantly, considering the complexity of these hybrid quantum classical algorithms, will we even understand the quantum logic or the unique optimization path it used to find that answer? The machine might begin teaching us physics we don't yet know how to articulate. That's the real threshold we're approaching right now.
Something profound to ponder as these timelines accelerate. Thank you for joining us for the deep dive.